Okay, so first of all, on Friday we have our first quiz. That's just at the end of class, 10 minutes, something like that. And then on Monday is exam 1. And for exam 1, the topics will be up through particle kinematics. Yes. Yeah, just the rest of the particle kinematics problems. Well, I mean, I don't know if I might as well just assign them tonight, and then you just have to be familiar with them by Monday, you know.
So how do we know if we're sucking at our dynamics if we have a quiz on Friday, but then we don't know until Wednesday?
I guess there's no way. No.
Well, it gives you most of the solution, so.
Yeah. Yeah, right. If you can. Yeah. Yep. If you, so you're just trying to get to a point where you could explain the thought process to any of those homework problems. There are solutions to some, so you can check your work with those. And if you want to, bring your other solutions into office hours or make an appointment with me outside of office hours, we can do that, Oh yeah, that's true. That's a good point. That's right. So if you look at that's right. I think it's in a section called 2017 course notes. And yeah, if you page through those, a lot of times I ask, people ask questions about homework problems before class. Mm-hmm. And then on those old notes, you can often find solutions to the problems where my solutions are wrong in the solutions. So that's nice. Any other questions about the test? All right. Anybody have any homework questions? 18? Do you have it with you or anybody? Okay. Okay. Yeah, I don't know if have I assigned that one yet. Okay, so number 18. So you have an incline of 20 degrees. I don't think that even comes into it.
I looked, like I said, from last semester, it was completely different than what you had on the solution.
Okay. That symbol from now on is that's a red herring. So I don't think that 20 degrees comes into this problem at all. I suppose it does if you use like a standard. Oh, it does give. Well, oh, it does. So you will need that. Well, I'm going to do it like this, and then I'm just going to convert my answers because it's so much easier. So this object's rolling down. It has a radius of 0.05 meters. The angular velocity is it says it's rolling down, right? So that means that that 20 radians per second is just magnitude. It has to be going this way. And it's speeding up with an angular acceleration of positive, well, again, it's speeding up, so we know it has to be this way with a magnitude of 15 radians per second squared. And so in that coordinate system, the velocity vector of the ball's center is negative omega r 0, 0. And omega is negative 20. That is true, or in the plane, you can just think of it as counterclockwise is positive and clockwise is negative. Yeah, I mean, that is what the right-hand rule says in planar problems. If you want to think of it in terms of the right-hand rule, yeah, your thumb's going into the page, so it's negative. X cross y has to equal z, so the z-axis has to come out. And so into the page has to be negative. So negative 20 times 0.0500 and 20 times 0.05 is just 1, right? So 100 meters per second. That's in that rotated coordinate system. So 100 in this coordinate system, you need to think of what that would be in the non-rotated coordinate system. So if we're going, here's one of several ways to do it. This is the way I like. So if this is your coordinate system, and this angle is 20 degrees, and you want to rotate, re-express this vector in this coordinate system. In order to go from here to here, you have to go counterclockwise 20 degrees. So theta is equal to positive 20 degrees. And so the velocity vector in the new coordinate system is equal to cosine 20, sine 20, negative sine 20, cosine 20 times 10. I guess I did this in 2 dimensions instead of 3. And so you just get 0.94, negative 0.342. Mm-hmm.
Our vector is radius, sine, cosine for x and y.
Mm-hmm.
Where I can, like, I got this answer for the velocity. Where I struggled was with the acceleration.
Mm-hmm.
We use that omega cross quantity, omega cross r. Doesn't, it gives you values for x and y. I can show you
Okay. Right. Yeah, it should give you values for X and Y because it's centripetal. Okay, well, so the easier way to do this, I think by far, is just to use that rotated coordinate system. And so the acceleration is alpha cross r plus omega cross quantity omega cross r. Actually, so sorry about this. Let's just use the formula that I came up with before. So we have what we get is negative alpha r in the x direction, and then omega squared r, and would that be so that's going to be well, this is just going to be 0 for the center. Okay, so this is the answer that we came up with last time. And so this is equal to negative of negative 15 times 0.0500. And so that should just be positive 0.7500 meters per second squared. And then you have to re-express that in the coordinate system I gave. So the new acceleration is cosine of 20, sine of 20, negative sine of 20, cosine of 20 times 0.750. And so you get whatever 3/4 of these are. Any other questions about that? Any other homework questions you want me to go through? Okay. Let me do an example. So let's say that there's a hinge connected to a wall, and you have one bar connected here where this angle is 45 degrees. At the instant that we're looking at, this thing is going to be moving, but at the instant we're looking at, that's 45 degrees. And another bar connected to a pin joint, and this angle is also 45 degrees. Each of the lengths is 1 meter. And the angular velocity here is 10 radians per second. the angular velocity here is 10 radians per second. And let's say there's no angular accelerations. So this is moving with a constant angular velocity, each of these two pieces. And let's say there's a point, so we'll call this point A at the wall. This is B where they connect, and then C. And we want to calculate the acceleration of that point C. So what this is doing is this one's moving this way, and this one's going that way. So it's straightening out.
So are we just looking for the x component of c then? If c are the same y value?
We're gonna just do it in the full vector form, but you're right that since those are equal and opposite, it's only going to be, at least its velocity is only going to, yeah, I think its acceleration is just going to be in the x direction. I think you're right about that, yeah. We're not going to make that assumption or anything. That'll just come out. Any other questions about the problem setup? Okay, so we're trying to calculate what's happening at C. And notice that this is something that rotating rigid bodies, linkages, where rigid bodies are connected to each other, always work like this. This point C is in circular motion around B, right? So we can use circular motion to figure out what C is doing relative to B. But then we also, B is doing stuff. So in order to use the relative motion equations, we have to use the fact that B is in circular motion around A. So we're going to use circular motion to figure out the acceleration of B. We're going to use circular motion to figure out the acceleration of C relative to B. And then we'll use the relative motion equations. And that's what you have to do anytime you see something like this. I think in the problems, there's at least two problems where you have to use that relative motion approach for a linkage. Okay, so the acceleration of C relative to the ground, that's what we want. And that's equal to the acceleration of C relative to B plus the acceleration of B relative to the ground. So this one is circular motion of B, nope, of C around B. And this one is the circular motion of B around A. Okay, so first I'll find the acceleration of B. So the acceleration of B relative to the ground is equal to alpha cross R plus omega cross quantity omega cross R. We just have to come up with those values. Alpha is 0. Omega of that left body is that's counterclockwise angular velocity. So that's in the positive z direction. So R is equal to omega is equal to 0, 0, positive 10. And now R, it has a length of 1 from the positive x-axis to this vector is negative 45 degrees. So it's going to be 1 times the cosine of negative 45, 1 times the sine of negative 45. So R is going to be 0.7071, negative 0.7071, 0. So the acceleration of B relative to G is equal to 0 plus 0, 0, 10 crossed with the quantity 0, 0, 10 cross 0.7071 negative 0.7071, 0. This is I guess I just went right to the end. So all this, if you calculate it, gives you negative 70.71, positive 70.711, 0. That's meters per second squared. And now to calculate the acceleration of c relative to b, we'll assume that b is fixed. Pretend like b is fixed and just imagine this being a circular motion around that fixed b. So the acceleration of c relative to b is equal to alpha cross r plus omega cross quantity omega cross r. Alpha is 0. Omega this time is the opposite direction, so 0, 0, negative 10. And r goes from the center of the circular motion to the point you care about. So in this case, from the positive x-axis, it's positive 45 degrees. So r is equal to positive 0.7071, positive 0.7071, 0. So the acceleration of c relative to b is equal to 0 plus 0, 0, negative 10 cross quantity 0, 0, negative 10 cross 0.7071, 0.7071, 0. So now the circular motion that we're doing is, with this is the center, and this point moving in a circle around it. And so the vector from the center of the circular motion to here has a positive x and a positive y. Yeah, I'm using this usual coordinate system like this. And if you calculate that, you get negative 70.71, negative 70.710. So now you have the two pieces of the relative motion equation. So the acceleration of c relative to the ground is equal to c relative to b, which was negative 70.71, negative 70.710, plus the acceleration of b relative to the ground, that was negative 70.71, positive 70.710. And so you get negative 141.42 and 0, 0.
Is that assumption accurate if the only assumption of it only going in the x direction if the rotations are the same?
And the lengths are the same, so I wouldn't even bother trying to think of that as a case. It takes too much. I would just, these problems, you have the information to do everything in vector form. Like if those angles weren't the same, or these angular velocities weren't the same, or the lengths weren't the same, then that wouldn't happen. It happened just because of all this symmetry. Because, well, yeah, so if we calculated the velocity, it would be moving to the right. But the acceleration is centripetal acceleration in both cases, so it's going that way and that way. But let's calculate the velocity, because so the velocity of c relative to g is equal to the velocity of c relative to b plus the velocity of b relative to the ground. The velocity of b relative to the ground is omega cross r. We already have both of those. Omega was 0, 0, 10. R was 0.7071, negative 0.7071, 0. And so the velocity is positive 7.071x, positive 7.071y, 0z. Then the velocity of c relative to b is omega cross r. And that's 0, 0, negative 10, crossed with positive 0.7071, positive 0.7071, 0. And that's equal to 7.071x, negative 7.071y, 0z. And so the velocity of c relative to the ground is those two added together. So that's 14.14200. So that point C has a velocity in the positive x direction because that contraption is straightening out. But the accelerations are in the negative x direction because those accelerations are all centripetal. Any questions about that one? Okay, what do you think? Do you want to do another like linkage type problem, or done with that? Enough of that. I don't know about that.
So there is going to be a linkage problem on the exam.
There's a good chance there will be, yes.
Yeah, we should do it.
Okay.
Just in case. But you suggesting it just proves that we should probably.
Yeah, okay.
Depends on who suggestions come from. I learned that the hard way. Oh, pot's not that bad. You're not drunk yet.
That's probably not even a real police car. I bet those were both the same guy making both of those two suggestions.
You have to tell you. The funny, sad part
I believed that until just this second. Now I don't know what to believe. Huh. Legally, or they can just lie and then... Huh, I didn't know that. I totally had bought that one. I have had that experience, but I always thought that they could lie because then later they'd just be like, I didn't say that.
You know, kind of disregards the whole undercover cop,
Mhm.
scenario.
Yeah. Okay, so let's say that this has a angular velocity of 5 radians per second. This one has an angular velocity of 50 radians per second. So this one is doing 10 rotations for every 1 rotation this one's doing. No, but we don't care about what it does over time. We just know that at this instant, that's what's going on, you know? All of these are just single instant calculations because the R vector only represents a single configuration, you know? And let's also say that this one is speeding up at this instant with an angular acceleration of 100 radians per second squared. And we want to calculate, so if this is, we'll call this A, this B, and this C. We want to calculate the acceleration of that point C. And I mentioned before that the reason that we usually will want to calculate the acceleration is that acceleration is the way you get from kinematics to loads. And so if you have something with a certain mass there and you want to know what kind of force that thing is going to be feeling, you need to figure out its acceleration first. So the acceleration of C relative to the ground, that's the acceleration of C, is equal to the acceleration of C relative to B plus the acceleration of B relative to the ground. The acceleration of C relative to B is alpha cross R plus omega cross quantity omega cross R. Alpha is 0, 0, 100. Omega is 0, 0, 10. And what? I am first doing the acceleration of C relative to B. So we're talking about, oh, it is 50. Oh, yeah. Sorry. Thank you. And then R. What's that R vector going to be? Yep, 0.5. 0, 0. So it doesn't matter that this thing is a meter long because the center of the rotation is this. Okay.
Just assuming that it's in the middle. That
Yes, I am assuming that.
I would also.
If I, yeah,
But in reality, it's probably dead center.
well, I made this up, so it's very likely. So 0.500. So the acceleration of c relative to b is 0, 0, 100 crossed with 0.500 plus 0, 0, 50 cross quantity 0, 0, 50 crossed with 0.500. This one is 0, positive 25, 0. This one is 0, positive 50, 0. And so this comes out to be 0, 50, 0 plus that would be 1250 in the x direction, negative, right? And so that acceleration is negative 1250, 50, 0. Meters per second squared. And now the acceleration of b relative to the ground there's no alpha. So now we're talking about the circular motion of B around A. There's no alpha. Omega is positive 5. Well, this is alpha is 0. Omega is 0, 0, 5. And the r vector is from the center of the circular motion, that's A, to B. So that's 2 meters in the negative y direction. So the acceleration of B relative to G is 0 plus 0, 0, 5 cross quantity 0, 0, 5 crossed with 0, negative 2, 0. The parentheses gives 10, 0, 0. And so altogether that gives, I think, 0, 50, 0. Yeah, that makes sense. Nope. Yeah, just identify the center of the circular motion, write down your alpha, omega, and r, and then just,
I feel smart again.
yeah, nice. I love that feeling. So then the total acceleration of c relative to the ground is equal to, what do we have up there? Negative 1250, 50, 0. Plus 0, 50, 0. So the total acceleration is negative 1250, 100, 0. If you were positioned on the end of that thing, would you live? No. Yeah, you would, but no one else. That's what, like over 100 G. Yeah, can't do it. Not gonna do it. Wouldn't be prudent.
So is that a Dana Carvey or a George Bush?
That's a Dana Carvey doing George Bush. Yeah, it wasn't very good. Impressions. That's the great thing about impressions. They can, even if they're terrible, sometimes they can be funny because they're so terrible. It's win-win. Okay, so I wanted to say one more thing about this. So this is how you do linkages, linkage problems, except that later on we're going to spend a ton of time working on linkages like this. So imagine a linkage like this, where this is rotating this way, and this one is rotating, yeah. Okay, so
That's a useful one.
So the ones in a plane we can do. The ones where all the motion isn't in a plane, we can't do. We'll be able to later, but these are a lot more complicated. So why is that though? Because it's not a problem with the number of dimensions. It's not like we're only doing 2D problems. You know, we're already doing everything in a full 3 dimensions. So why does this affect anything? Well, the key is that so you have one motion riding another motion, right? We had that in the planar case too, though, and that worked out fine. But in this case, the axis of rotation of the one that's along for the ride changes based on the rotation of this one. In the problems that we can do, that's not the case. Okay, but like as this one moves, the axis of rotation changes, and that affects the angular acceleration and angular velocity of this one. So if I put one on the test like this, just say like we can't do it, and then you're done. I won't do that. But just notice the difference for now, and then we'll spend a lot of time later working on these. And then if one day it occurs to you like, wait a second, we already did the linkages, like what's the deal? That's the deal. It has to do with What makes it hard is if the axis of rotation of one of the bodies depends on the motion of the other body. At what time during the semester? Towards the end. Not that far towards the end. We still have a few things to do after that. But those problems are cool. Like, that's interesting stuff. This actually is, yep. And in order to do calculations like this, we'll have to learn how to do calculations in rotating coordinate systems. So we'll have to have a coordinate system that's riding along with the second one, and then we'll have to deal with the fact that that coordinate system is not inertial. Yeah.
Like I was getting bored with the whole like